the discussion that we had at the beginning of our last class was, well, how do you know when it's math? So what does math look like? What is it that makes all these different areas of mathematics? What makes them all math? What do they all have in common? And so, problem solving is a big part of it. Patterns are a big part of it. Various possibilities for how mathematical objects can interact. There's logical reasoning involved. Numbers are sometimes there. I think we kind of went from the always position to the usually position to maybe the sometimes position. But what really kind of distinguishes it is that mathematicians study structure. We study what are the possibilities for what we can do with the objects that we bring into being by defining them in some logical process, right? And so the example we talked about last time was that as you start your development as a mathematician, starting from when you're 2 or 3 years old, you start learning how to count. Then you realize that there's a zero, and now you have more possibilities. Then you realize there are negative numbers, and you have more possibilities. Then you realize that rational numbers exist, and you have more possibilities. Then you go to the reals, and you have more structure. You go to the complex numbers, and you have more structure. And so we want to get to a point where what we care about as mathematicians is less about the specifics, about the numbers, and more about the structures, right? What properties do these things have that characterize them, and are there other mathematical objects that have that same structure? Right? Those are the kinds of questions that we want to be able to answer in a class like this one. Abstract algebra is the kind of class that I believe gets us probably as close as we get in our curriculum to the foundations of mathematics, sort of understanding how to unify the different kinds of mathematical thinking into the study of mathematics itself, in a sense, mathematical structures. And so the purpose of doing this rational tangle activity last time was to help you think about a structure that has, on its face, nothing to do with numbers, right? I didn't see any numbers happening on this screen here, right? So we introduced you to how to tangle up a couple of ropes using T, which is a twist of the upper right over the lower left strand, and R, which is a 90-degree rotation of the whole thing, the whole tangle, counterclockwise. And by spelling out a word using T's and R's, we were able to construct tangles of varying complexity. And along the way, we made some conjectures about what structure is actually underneath what's happening here, right? Questions like, well, how do the T's and the R's interact with one another? One of the hypotheses one of the things we noticed was that there were different names for the empty tangle. We could just call it empty, or we could call it TRT, because if we started with an empty tangle and did T and then R and then T, that happened in this dance right away, right? We found out that even at that stage, the tangle was already empty again. And when you continue doing RTR after that, this 6-letter word also represented an empty tangle. And more than that, this, was it 12-letter word, also represented that same empty tangle. So clearly there's some structure underneath here that makes this long, complicated-looking word actually correspond to a very simple, in fact, the simplest possible object in this mathematical system. So different names for the same thing. So there's got to be some structure. There's got to be some ways in which the T's and the R's interacted. And the last example that we did in our first class was taking a rather complicated tangle, so this set of 15 letters tangled up into something that looks like this, but then showing that if we continue using R's and T's in this particular sequence of 12, I think, letters, that it actually untangles the whole thing, right, and gets us back to the empty tangle. So now that you've had 47 or so hours to think about it, maybe you slept a little bit in there, I hope. What else, what other conjectures, what other ideas did you come up with, or maybe what other kinds of equations might you be able to write with T's and R's that tell us something about the structure that we have? So what did you say? The first observation you made was that to reverse a rotation, we have to do 3 rotations. How did you know? How do you know? Why does it work that way?
If you do like 1 rotation.
Given that our R is a 90-degree counterclockwise rotation, if we continue and do 3 more 90-degree rotations, how much have we rotated in total? 360. And if we rotate our tangle 360 degrees, we know we're going to get our original tangle back, right? Because 360 degrees is a full rotation. Can we turn that observation, maybe I'll write it like this, 90 plus 270 equals 360. Can we turn that into an equation that involves just T's and R's and not numbers? So what does this mean about the structure of the T's and the R's? So we would write that out by just writing a total of 4 R's. So R, 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 R. And what would that then equal? it would equal, right, it would equal an empty tangle, right? Or at least it would somehow, whatever we're using as our placeholder for nothing happens, right? But that set of 4 r's in a row we would call empty. And it doesn't really hurt, I suppose, to use a little bit more compact notation for a series of 4 r's written in a row. What would be a smarter way to use notation for that? Or what does this resemble? I mean, if these r's were numbers, what would this look like? What would be another way to write it? R to the fourth power. Yeah. So this, by the way, is the notation that we're going to most commonly use in abstract algebra for when we take elements. These t's and r's, we're going to call them elements, right? We take elements and we compose them, operate on them, glue them together in a series. If it's all the same ones in a row, we'll just use an exponent. At least in the beginning, it's going to be a natural number exponent to represent that product of 4 things. Right? So we can call that r to the 4th. So that's an equation that kind of tells us about the structure of the r's a little bit. R to the 4th is going to be an empty tangle. I'm interested in the second observation. Because the question you asked yourself when you were describing this, you said the question we were asking ourselves is, how do you untwist a twist? And your conjecture here is that RT be an inverse twist. Right? Can it undo a twist? So what's the evidence for that? What's the evidence for TRT equaling empty? So the evidence for that is that in this middle dance here, TRT, as the first 3 steps of the dance, already got us back to an empty tangle. So it would seem that if we want to untwist a twist, what we should do is rotate and then twist. Right? And that we should cancel it out. But here's a question. If that were true, let's see if we can find, well, is there any other place here? So this RT here, we would assume, also would have canceled out that T. And where is there another one? But then this RT would have canceled out that T. Okay. And then we'd have, all right. So maybe let me make this point out of this observation, is that these rules, these structures that we're coming up with here, what we want them to be for us is we want them to be a way to simplify a rational tangle dance word. If you give me a word that has like 25 letters in it using T's and R's, if we know something about the structure of the T's and the R's, we might be able to simplify that expression to be the same tangle, just in a shorter word, right? For example, if you told me this 12-letter long word, and you really meant the empty tangle, I would probably recommend to you, hey, why don't you simplify that? Why don't you just call it the empty tangle? Why bother with the long 12-letter word? Same thing with this word here, TTRR, TTRR, TTRRT. Right? That ended up being this tangle. Just by looking at this tangle, can you think of a way to simplify it? Is there a simpler dance that could have given us that tangle? So first of all, just looking at the tangle diagram, what we're seeing here is we're seeing 7 crossings. 1, 2, 3, 4, 5, 6, and 7. And each of those crossings could well have just been made by a single twist. Right? We didn't need to do any rotations to make this tangle. Right? So I agree with this simplification. We can simplify this expression down to t to the 7th power just by looking at the tangle. But then you said one other thing that I find interesting. You said, well, this pairs of r's looks like they canceled one another out. And indeed, if that were true, so I'm going to sort of modify this, is RR also empty? Question mark. If it is, then that means that we could simplify this expression just by canceling out those pairs of r's that are next to one another. And that would seem to jive with what happens with this, right? If I just cancel out all these r's that are there, then what's left over is just going to be 1, 2, 3, 4, 5, 6, 7 t's. But wait a minute. How many degrees is an RR rotation going to be? 180. So why would that be empty? The questions we're asking ourselves are all intended to get to the structure of the T's and the R's in ways that will help us to do 2 things. One of them, to simplify expressions. Right? If I know, for example, that RR is empty, then I should be able to just cancel out any RRs that I see and simplify the word that I'm working with. Same thing with TRT. If I know that that's an empty tangle, then any place I see a TRT, I can just cross it out. Right? So we want rules for simplifying. Well, we're going to want some rules for solving equations. Because if there's one thing that makes algebra its own particular kind of math, it's simplifying expressions and solving equations using structure. Right? If I could give a one-sentence description of what abstract algebra studies, I think that's it. Right? It's math because it deals with all the things that we talked about in the first slide. But it's algebra particularly because it gives us ways to simplify expressions and solve equations that depend only on the structure and not on the particular types of elements and objects that we're working with. Right? So, coming back to it, we know kind of two things now about r. We know that r to the fourth power is empty. R to the fourth, just we can cross it out. But then we also have this question mark here. Maybe r squared is also empty. Okay, so these are two logical propositions. Does one of these imply the other? Are these logically independent positions, or does one of them guarantee the other to be true? If I knew that one of these things was true, would the other have to be true? Why? So your claim here is that if we already know that r squared is empty, that would imply that r to the fourth is empty. Why?
Because you're just doing the same thing twice. So if you have an empty tangle and you just do what you did twice to make an empty tangle, then you
Okay.
just have it.
Right, exactly. So if r squared truly is empty, then r to the fourth, which is r squared squared, right? It's just r. We could cancel out each of these r's in its own pair and just make empty times empty, which we would expect to be empty. Right? What about the other direction? If we know the fourth power of r is empty, can we say that the second power of r is empty? Not necessarily. So if we were thinking about, if we weren't thinking about tangles, if we were just thinking about any kind of geometric object, right? Every geometric object that we can rotate, by the time we rotate it at 360 degrees, we get the same thing again. But there are a lot of geometric objects which when you rotate them by only 180, you get something different. So probably doesn't go the other way. So knowing that r squared is empty is a stronger statement, because it will then imply that r to the fourth is empty. What other powers of r would have to be empty? Which powers?
Even powers.
Any even power of r would then have to be empty. So r to the power 262 would have to be empty, right? So knowing that r squared is empty is super, super useful. If it's true, and it actually takes a bit of doing to prove that it is in fact true, that the evidence that you see here in this example is in fact illustrative of the general case. It is true that r squared is empty for any rational tangle, which in the beginning it's not obvious why that should be. But if you just took this tangle here, I think I can actually do this on the screen, let me try it. If you take this tangle here and you just rotate it by 180 degrees, so there we go. There it is, rotated 180 degrees. Well, it looks like the same tangle, right? It just has the 7 horizontal twists going from left to right, each one of them created by twisting the top right over the bottom right. So at least for that tangle, it looks like rotating 180 degrees does nothing. But what's more interesting is what about a sickly-looking tangle like this one up here, something that's really complicated? If I rotate this thing 180 degrees, why should I expect to get the same tangle back? And that's a question that I don't want us to answer right now. If we were in a course that studies rational tangles for their own sake, such as the seminar that I taught on knot theory in algebra at the end of the year last year, that's when we could really get into these great details about why, for these particular kinds of objects, these tangles, why is 180-degree rotation actually still give us the same tangle back? And there's a really nice mathematical induction proof for why that's true. The question about how to untwist a twist is much more interesting. And this conjecture that TRT will always cancel is one that I want to tug on a little bit more. It certainly seems true that if we start with an empty tangle and then do TRT, we end up with another empty tangle, like this one here in the middle. But here's my question. I'm going to just reframe the question a little bit. So does RT cancel a T? What we're really asking here, let me reframe this as an equation problem. If algebra is about simplifying expressions and solving equations, what I'm asking is, if I have the equation T x equals empty, and I solve this for x, then I think we can convince ourselves that x equals RT is a solution. Right? But, sort of similarly to our question about r to the fourth and r squared, could there be a better explanation for how to cancel the t, how to untwist a twist, right? So why don't we try this? Let's suppose that I take a more complex tangle. Let's say T, T, R, T, T. And let's say I want to know what I can put here, what x I can put here, that will just cancel out the t that's sitting next to it. Right? So if this x cancels out that t, then how would I simplify this expression? What would I get on the right-hand side? TT, Well, if I substituted RT in here, then yes, I would get TT, RT. Oh, let me just write that for now. TT, RT by making that substitution. Right? And if it's true that this RT cancels T, then this TRT, our conjecture is, would just cancel out. And so we should get TTRT. All right, so let's test our conjecture. And when I say test our conjecture, I really do mean I need 4 volunteers again. Let's make up these tangles and see if we really do get, see if TTRT is the same as TTRT.
I have a question.
Yeah, great observation. So now that we've canceled out this TRT, we've noticed that, oh, there's another TRT sitting here, right? And we could say that this RT here, if it's true that RT cancels T, then we could keep going. And we would only be left with just T. All right, so if it's true that RT cancels T in the way that we say, then if I did this rational tangle dance, at the end of the day, I should be left with only that single horizontal twist in the middle. All right, want to try it? It does not appear that this RT was successful in canceling this T, and that RT in canceling that T. So we must need something stronger, right? We must need, if it's true that we can untwist a twist, and by the way, do we believe we can always untwist a twist? Why? Why does that seem reasonable based on what we did on Wednesday?
Because we ended with an empty set.
We ended with an empty. Even when we started with something super complicated, we were able to do the same T's and R's to cancel everything out and end up with an empty tangle. So it does seem possible to untwist a twist, but just RT by itself doesn't seem powerful enough in this example. So we might have to do more. Let's borrow. So now that we've decided that RT is not enough to cancel a T, what we want to do now is think about taking what I'm going to call a generic tangle. So it looks like this, right? And if somebody puts a twist onto here, so then it's going to end up looking like this. So go ahead and do a twist. And so we call this new tangle GT, right? Now the question is, how do we cancel out this twist? So at every step of the dance we're about to do, the question is, do I want to twist next or do I want to rotate next? So what do you think? If we want to get rid of that crossing over there and get us back to the original tangle, should we start with a twist or start with a rotation?
Rotation.
Why not a twist?
Because then you just have 2 twists.
Yeah, twist is just going to make things worse. It's just going to add a second crossing over here. So that seems like a good idea. Let's rotate. Yeah, we don't want to follow a rotation with another rotation if we believe that the R's cancel in pairs.
Twist.
So let's do a twist instead. Right. Do me a favor and pull your rope a little bit more if you can. If the board flips over a little bit, that's okay. Yeah, there we go. Keep going. It's okay if it flips over. You're right. So it doesn't, again, seem like this is the same as my original tangle, right? Because if you can read the word tangle, if you're looking at it this way, we've got some extra crossings going on. And if we don't, then we have the word tangle is backwards. So again, this RT did not cancel out that T. If it did, we'd have our original tangle back. All right, so what do we want to do next? Twist or rotate? Why is twist a good idea? All right, so we rotated. Are we back to our original yet? Doesn't seem like it. So what's next? Another twist. Because if we did 2 rotations in a row, they would cancel. Oh, look at that. What just happened? So to get us back to our original tangle, once we added a twist, the first RT didn't do it. The second RT didn't do it. But adding another R after the end of that did. And it didn't matter what twists and turns and everything existed inside of G, right? Because in our example, this is just a big cardboard square, rectangle. So what do we conclude about how to untwist a twist? What do we need in order to cancel T? Yeah, we need not a single RT, but RT, RT, R. Right. So if we sort of take stock of what we know about the R's and the T's at this point, the R's were relatively straightforward. R squared is empty. And so R cancels R. Right? R squared equals empty sounds like a simplification rule. R cancels R sounds like something you could use to solve an equation, right? Because if I'm trying to solve an equation, I'm trying to cancel things away from my x that I have on one side. So that's the first big observation. And the second one that we just won is that TR, TR, TR is empty. And so RT, RT, R cancels T. So here's a question. Let's suppose that I want to solve this equation. I'm going to give your groups a few minutes to think about this. If I want to solve the equation TRTTX equals, let's say R. If I want to solve this equation for x, how to do it? So now that we know these rules that are up here in the box, get your heads together with the other 3 people around you and see if you can figure out what value x should have to solve this equation. So the point of algebra, how we solve an equation in algebra, is we apply a canceling operation to both sides of the equation. And we try to choose those canceling operations strategically so that after we cancel, we're that much closer to isolating the variable. Right? And if we do enough of those canceling operations, eventually the variable will be by itself. And on the other side of the equation is the value that that variable must take. So see if you can come up with a systematic way to cancel from both sides, using what we know about T's and R's, to solve this equation. All right, so the first thing you did when you looked at this is you said, well, TRT is an empty tangle. So that means, based on that, what did you do next? Okay, so you crossed it out. Okay, it's the empty tangle. So this is now just Tx equals R. All right, then what happened after that?
You have to cancel out the T, so you have to do the RT.
Right, so we know that RT cancels T. So what did you do with that fact? How did you use that?
We just had
Read off your next line, I guess.
RT, X equals RT, R, R.
Okay, X equals. So it was the. Okay, so this R is over here, and then you have RT here in the middle. Okay. Did you do anything after that? I'd argue there's one more thing we could do with this answer. What if I wanted to simplify it? Yeah, that pair of R's right here would cancel. So according to that, I would end up with just X equals RT. Is this what everybody got? Did people get something different?
I got like.
So in this thought process here, the RT. So let me ask you, why did you put RT on the left of the R in this? Why did it show up here?
Because your undoing the t.
You're undoing the t, and in order to undo the t, your idea was take RT and apply it to the left side of this expression,
Just an r. Yeah.
and then also to the left side of this expression, right? And then when you did it, you applied it on the right sides. So if I applied it on the right side, let's think about what that would look like for a second. Maybe I could just back up. If I applied it on the right side, then
Oh, it wouldn't directly cancel the t.
yeah, it wouldn't directly get to the t. So RT would go here, and then RT would also go here. So while this is still a valid in the sense that it has the same truth value as the original equation because we did the same thing to both sides, right? It doesn't help to cancel that t if it's sandwiched on the other side of the x. Why do we need to be fussy about this? I don't think we've ever had to be fussy. Well, we may have had to have been fussy like this before. Is there any other class or any other situation in which you found yourself having to worry about left side versus right side?
Analysis.
Linear, yeah, I'd say linear algebra. Analysis maybe, but linear algebra more so. Because what's the problem in linear algebra? Like, why do we have to be so scared about left side, right side in linear algebra? What are playing the roles of T and R in linear algebra? What kind of objects? Matrices. And why are matrices different from real numbers in this kind of process?
They have dimension and stuff.
They have dimension. So the addition and multiplication that they do with one another, they follow slightly different rules, right? In particular, what is the property that the real numbers have that makes us not have to worry about left side versus right side when we do an addition or a multiplication or something like that? I'm not done with this example yet, but I'm just curious. I'm trolling for a buzzword here. If it didn't matter, right, if I could put this RT on the right side instead of the left side, and then just slide it past the x so that it could connect to the t and cancel, what property is that called? Close. It's still close. It's the commutative property. If we had the commutative property, if we could take for granted that it didn't matter which order I wrote my word, right? Then, for example, if this were commutative, then RT would be the same as TR. And RTR would be the same as TRR or RRT or any of those things, right? If we had the commutative property, we could just flip-flop the left and right ordering all day if we wanted to. But what do you think about these T's and R's? Do we know they're commutative? Because if they are commutative, then we don't have to worry about this stuff. Do we have any evidence of whether or not T's and R's are commutative in this setting? We have evidence that TR and RT are in fact different, one from another, right? So we can't, even that one single counterexample, by the way, that one bad apple, spoils the whole bunch. It means any manipulation that we do with these T's and R's, we cannot take for granted the commutative property. If we could, our life would be a lot easier. And commutativity is going to be one of the things that we work very hard this semester to try to win back from the void. But for now, we cast it into the void. The structures that we study, we can't take for granted that they're going to be commutative. Which also brings me to one last point that I want to wrap up with. We said that RT cancels T because of this equation. But in order for RT to cancel T in this equation, take a look at where the RT is happening. On the left side. So the question that I want to pose here to give you to talk about over the weekend, and jump into Slack and make some educated guesses. Is it true that RT cancels T both on the left side and also on the right side? Because if we can be sure that RT cancels T on the left side, in other words, that this word is equal to the empty tangle, then it seems like this is a good solution to this. But we don't know that for sure. So is it possible, maybe this is the question I want to ask, can something that cancels on the left not cancel on the right? Can something that left cancels fail to right cancel? So maybe what I'll ask for you to think about on Slack is, can you find an example, either in this rational tangle universe, or maybe in some other mathematical structure that's out there, where we have an object, an element, that has something that it cancels it on one side, but that thing doesn't cancel it when it multiplies on the other side?